Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
In the silent, glowing heart of our modern civilization, there is a metal that works tirelessly behind the scenes, protecting the very structures we live and work in. It prevents our bridges from crumbling into dust and keeps our infrastructure standing against the relentless, corrosive force of nature. It powers your remote controls, your high-tech medical devices, and even the next generation of massive renewable energy grids. It's even essential to your very existence, a critical mineral for your DNA, your brain, and your immune system. Yet, to find it, we must journey kilometers beneath the surface into the Earth's dark, high-pressure crust, where nature hides its treasures. This metal is zinc, and today we embark on the definitive 15-minute masterclass covering its complete industrial and biological life cycle. Welcome to Simple Gyan. I'm your guide through the engineering secrets of one of the world's most vital yet overlooked metals. In this deep dive, we'll analyze everything from mineralogy and mining to chemical roasting and high-purity electrolysis. We'll also look at the future of zinc in green energy and its 100% recyclability. Let's begin the journey. Chapter 1. The Atomic Blueprint. To understand zinc's power, we have to look at its very structure on a molecular level. Zinc is a transition metal with the atomic symbol Zn. It's part of group 12, sharing properties with cadmium and mercury. With two valence electrons, zinc easily loses electrons to form Zn2+ ions. This is the fundamental key to its corrosion protection. Chapter 2. Geology and Minerals. How does nature create this resource over millions of years of tectonic activity? Most zinc deposits were formed by hydrothermal activity, hot fluids rising through cracks in the crust and cooling to deposit minerals. The most common ore is sphalerite, or zinc sulfide. It accounts for about 95% of the world's zinc production. Secondary sources include smithsonite and hemimorphite, formed by the oxidation of primary sulfide ores over eons. Zinc is found globally, with major production hubs in China, Peru, Australia, India, and North America powering industry. Chapter 3. The Art of Mining. Extracting these ores requires some of the largest machines ever built by mankind. Open-pit mining is used when the ore body is near the surface, allowing for massive production volumes and efficiency. But many high-grade deposits are deep underground, requiring shafts reaching over 2,000 meters into the crust. Underground, we use sub-level stopping, where huge rooms of ore are blasted and removed from below safely. Modern mines are increasingly automated. Robotic loaders can be operated from a distance, keeping miners out of harm's way. Mining in the Arctic, like the Red Dog mine in Alaska, requires incredible seasonal logistics to ship ore before the sea freezes. It starts with crushing. Gyratory and jaw crushers use hundreds of tons of force to reduce the ore to a manageable size. Secondary ball mills then pulverize the ore in water, creating a slurry where every particle is finer than sand. Chemical collectors coat the zinc, making it water repellent so it attaches to rising air bubbles in the tank. The valuable zinc floats to the top as a foam, while the waste gangue rock simply sinks to the bottom. The waste rock is pumped into tailings dams, ensuring environmental safety and the containment of processing water. The collected foam is thickened and dried into zinc concentrate, now at nearly 60% zinc content. Chapter 6. Roasting. We now change the chemical nature of the concentrate from sulfide to oxide with high heat. In fluid bed roasters, air is blasted through the concentrate, burning off the sulfur at nearly 1,000 degrees. The process releases sulfur dioxide. Modern plants must capture this gas to prevent atmospheric pollution and acid rain. The captured gas is turned into sulfuric acid, a valuable byproduct that makes the refining process more economical. What remains is calcine, a high-grade zinc oxide that is now finally ready for the actual metal extraction. Now we reach the industrial heart. Electrolysis is where pure electricity takes over to refine the metal. But first, we must dissolve the solid calcine into a liquid. This is the leaching stage, where acid meets oxide. In leaching, zinc oxide dissolves in sulfuric acid to create a highly concentrated zinc sulfate solution. Even tiny traces of copper or cadmium can ruin the electrolytic process. Purification is absolutely critical. Zinc dust is added, causing other metals to precipitate out, leaving behind a pristine, purified solution. The purified solution is pumped into the tank house, where electricity performs the final molecular work. Electric current pulls zinc ions from the solution, depositing them onto aluminum cathodes as pure metal. Every few days, the cathodes are harvested and the pure zinc is stripped from the aluminum for melting. The sheets are melted and cast into various industrial shapes, including massive 1-ton jumbo blocks. This is special high-grade zinc, the global industry standard for over 99.99% purity. The imperial smelting process uses a specialized blast furnace to produce zinc and lead simultaneously. Zinc gas is captured by a rain of molten lead, condensing it back into a liquid form for final refinement. Chapter 9. The Power of Alloys. Zinc's true versatility is found in its chemical partnerships. Brass, a copper-zinc alloy, is vital for high-end plumbing, acoustics, and precision musical instruments. We've covered an immense amount of ground today, from geology and mining to the high-tech chemistry of electrolysis. Understanding these hidden industrial processes gives us a profound appreciation for the engineering that builds our world. Thank you for joining me.